welcome to the solutions for the circle theorems problem. One of my favourite topics this. So we've got a circle here. Notice the diagram's not accurately drawn. I'm pointing this out because there's always somebody who tries to solve these by measuring. You can't use your angle measure on it. And it tells us that A, B and C are points on the circumference of a circle. Well, we can see that. The centre is O, we can see that as well, and AC is a diameter of the circle. That's important. Write down the size of angle ABC. Well, it's 90 degrees. How do I know that? Well, without going into too much detail, there is a circle fact, and the angle in a semicircle having trouble writing circle tonight. CIR is 90 degrees. And with those few words disguising a fascinating fact that if you put a diameter across any circle and then draw a triangle on it, you will have a right angle triangle. That is how you can make a right angle without an angle measurer. Fascinating bit of maths. Here's another one. Okay, D, E and F are points on the circumference. Yes, we can see that, we can see that, we can see that too. Work out the size of angle DEF. So there's DEF, so that's this angle here, and that angle there is half of the 130, so it's 130 divided by 2, which should give you 65 degrees. And the angle, the reason is the angle at the centre is twice or double the angle at the circumference. Another fascinating fact that is conveniently glossed over by the GCSE syllabus. Why is it? Very interesting. Well, there's a way to show it. We will do that at some point. Okay, well that's a nasty looking diagram, that is. Let's just have a look at it before we read the question. I mean, there's several tempting looking right angles here and here, but you know, are they right angles? Maybe. However, there is one definite right angle, that's this one here, and I know that's a right angle because it tells me down here that DA is a tangent, and the angle between a tangent and a radius is a right angle. So let's see what we've got to do. Work out the size of angle AOD. Okay, that's this one here, A to O to D, it's this angle. And we can see that since this is 90 and this is 36, 90 and 36 make 126, and the angles in a triangle add up to 180. So 180 take away 126 is 54, I believe. Let's double check that. 54, 60, 70, 80, lovely. So it's 54 degrees. And the reason, well, there's two parts to the reason really. Okay, number one, 90 degrees between tangent and radius. And number two, 180 degrees in a triangle. And this is the key really to these, is just to think the steps you took to get to your answer and just write down your reasons for each of them. Now we've got angle ABC, so let's go back up to the diagram and identify it. ABC, that's this one here. Now, please don't think that these are immediately obvious to everybody, because they're not. They're actually they can take a while to get, and this is quite a tricky one really. The key is to spotting some patterns. Now, I'm just going to run through the patterns that I look for. First of all, I'm looking for the triangle in a right angle, the right angled one there, the one we saw above. That's clearly not the case. We don't have a diameter here. After that, I would probably be looking for something like the hourglass problem, like this one. Okay, so those two angles would be the same. It's not that, because this has got something at the centre, and this is the clue to it here really, because this is basically the Star Trek fact which we had in the problem above. The angle at the centre is double the angle at the circumference, only this point here has been moved round so that it looks like this. And you can see that's what we've got here. So angle B is the angle at the circumference, and this is the angle at the centre. So angle B is half of angle O at O. So 54 divided by 2 is 27. So it's 27 degrees, and the reason is the angle at the centre is twice or double the angle at the circumference. The key to being good at these really is practice, but it's also to think of this as a pattern spotting exercise. Several other things that might help. Well, don't try necessarily and go straight for the angle they want you to. See what other angles you can work out. That's something which is sometimes a good strategy. But yes, practice is the key. Now the challenge question. A, B and C are points on the circle with centre O. Okay, boring, boring, boring. Prove that the angle subtended by arc BC at the centre of the circle is twice the angle subtended by arc BC at point A. So that's a complicated way of saying the fact we used earlier, and we've got to prove it this time. So here's arc BC, and as you can see, there are two angles subtended or standing on it. So the one at the centre of the circle, that's this one here, that's standing on it. And this one up here, this is also standing on the same arc. So that's all it means. So how do we prove this? Well, first we're going to have to use the properties of triangles and circles. So the first thing I'm going to do is I'm actually going to draw in a line here. This is often a good move in circle problems. This line here is a radius, which means it's the same size as all the other radiuses. Okay, so I'm going to write down AD equals AC equal, sorry, OC even, let me get that right. Let's get it right, shall we? Apologies. So A to O, because O is the centre, is the same as C to O, which is the same as B to O, and they're all radii of the circle. And they're all equal. Now, what's the next thing? Well, let's call this angle X, in which case this is angle X here. Alright, because it's an isosceles triangle. So angle A to not A to O, sorry, let's get it right. So this angle here we'd call CAO maybe. CAO. So angle CAO is the same as angle, OCA, should we say? OCA, and it's because it's isosceles triangle. And then similarly over here we'll call this one Y, shall we? So angle OAB equals angle OBA, and the same reason, isosceles triangle. Now, what that means is we can work out this angle here. So let's call that P, shall we? So angle P is equal to 180 degrees minus 2y, and angle, let's call this angle Q here. Angle Q is equal to 180 degrees minus 2x. Alright. So now we look at this whole angle here. So the angles about O even, add to 360. So let's call this one, I don't know, let's call this one angle N. So N plus P plus Q is equal to 360. So N, now P was 180 minus 2y, and Q was 180 minus 2x, and that adds up to 360. So now I'm going to simplify, so N minus 2y minus 2x is equal to 360 minus 360, which is 0. That's because I've subtracted these 180s across there. So now we're going to add these across so that N equals 2x plus 2y, which is 2x plus y, which is the angle here. So we can conclude now. So the angle at N is equal to 2x plus y, that is, i.e. double the angle at point A. If there's anything about that you don't get, which I have to say is fairly reasonable, then feel free to drop me an email and I'll explain it. But what we've done is, by not using any numbers in this, we have generalised it. This would work for any number, and you can see that that no matter what numbers you put in for x and y, these two have always got to be the same because it's isosceles. This one here always has to be the leftover from 180, and the same for this triangle. And when you do the algebra, you can see that the angle here always works out to be twice these two angles here added up. So whatever this one is, this total angle here is half of it. Hope you found that interesting, and we'll be back for more.